As a third topic of today, we'll discuss about bending of composite member problem. So here, let me think about like one simple example with rectangular cross section. The front view, you can see the top part is given as red block and the bottom part is given as white block. So there is two different material, and the cross section looks like this. So if we recall the assumptions we made about the pure bending, what you can see is the cross section, yeah, located and oriented with a 90-degree angle even after bending, and they're gonna meet at one point if we extend their planes. Okay, so what you can see here is that under pure bending, uh, uh, like regardless of the material, what you can expect is, yeah, because normal strain is simply obtained by the ratio between the original length and the current length. Yeah, we can see that the normal strain must be simple linear function if we know the the position of neutral axis, right? So this is what we can see regarding the strain. However, even though we have like this simple linear strain relationship, we're gonna have a different stress in different material. Why it is so? When obtaining the stress for material 1, we have to multiply E1. When we have to obtain stress for material 2, we have to multiply E2. Okay, so yeah, this is EX part, this is EX part, and we have to multiply modulus. Then suppose that for our example in previous page, and we have two different modulus, E1 and E2, and suppose that E1 is smaller than E2. Yeah, you can see that up to the region of E2, yeah, we have this linear relationship, and like in the region of E1 with the red material, we have the multiplicative factor of E1. So we have like this interesting distribution of normal stress. Okay, so this is how we approach the problem when we have the information about centroid. However, if we don't have, no, it's not centroid because the composite problem, yeah, we cannot say centroid goes through a neutral axis goes through centroid because the material have two different Young's modulus, and we cannot apply the knowledge we developed in previous discussions. But let's just do specifically call neutral axis. Neutral axis means the location where the original length does not change under the pure bending. So once we locate the neutral axis point as y equals 0, then we can obtain the strain, and from strain we can obtain the stress distribution. So our first job to solve a composite problem is locating the neutral axis. So how can we do that? Yeah, so for that, yeah, we have to construct equivalent single material problem. Yeah, of course, there is a method to solve the problem as it is, but for ME231, because we want to offer simplest possible explanations on how to approach the problem, yeah, I will introduce a method of constructing equivalent single material problem. So here the idea is really simple. Suppose that you focus on one infinitesimal area dA, and the force on this infinitesimal area dA can be written as stress on this area, which is E2 times epsilon x multiplied by this infinitesimal area dA. So this is force acting on here. So equivalent to single material problem considers a problem with same force and moment distribution. To satisfy that, we have to make a single material problem whose force at same height must be same. To do so, we have to first obtain the ratio between E2 and E1. Here, we want to construct equivalent single material problem with red material with E1. So we colored the entire section with E1, and as I told you, we assume E1 is smaller than E2. If we define E2 over E1 as the ratio n, then for this single material problem, the stress is E1 times epsilon xy. Yeah, because E1 is smaller than E2, yeah, we're gonna have similar stress. But if we extend and widen the width of the y section, so that the originally dA area becomes NDA area, then if we multiply this, n is E2 over E1, then what you can see is it becomes identical to original problem. So what we do is like we just set one reference material, and having set the reference material property in the denominator, and put the other material property in the numerator, and considering the the ratio as n, then what you do is you simply widen or shrink the another material in the ratio of n. Okay, so that we can solve the single material problem. And after solving single material problem, what you're gonna do is we're gonna get normal strain distribution, which is simply linear function of y. After obtaining normal strain, you can apply the simple Hooke's law and multiplying E1 and E2 and to obtain a stress distribution. This is the logical flow. So let's solve one specific problem with composite made out of brass and steel. So the front view of our problem is somehow only red material, but when you see the side view and cross-sectional view, it has interesting cross-section. Here the steel in the center is sandwiched with two brass film at the front and the back side. Okay, so the width of the brass film is 10 millimeter each, 10 millimeter here, 10 millimeter here, and the width of the steel is 18 millimeter, and the Young's modulus is 200 gigapascal for steel, and Young's modulus is 100 gigapascal for brass, and height of the entire cross section is uniform as 75 millimeter. So if we consider the equivalent brass problem, we can do a quite simple job. So we first obtain the ratio between ES and EB, because we're gonna take brass as a reference material, and this ratio will be 2. So we simply extend the width of the steel by a factor of 2, such that we have 36 millimeter here, 10 millimeter here, and 10 millimeter here, so that the entire width becomes 56 millimeter. And we don't need to touch the height, so the height is 75 millimeter. And for this is equivalent to single material problem with brass property, we can obtain the value of I and the location of centroid really easily. Centroid is at the center of this rectangle, and if we obtain the value for I for this brass problem, it becomes this value. But you gotta be careful, like when you solve this problem using steel as the reference material, you're gonna have thinner cross section, because you use steel as the reference material, and you have to shrink the width of the brass, but then you're gonna have different I when you convert this into steel problem. Okay, however you don't need to worry about it. So when we solve the brass problem, when obtaining the strain, we have to use minus y m divided by modulus of brass multiplied by I of this brass problem. If you happen to use the steel problem instead of modulus of brass, we have to use steel elastic modulus and the I for that single equivalent steel problem. Then anyway, you're gonna find that the denominator will be same and strain will be same. Okay, so regardless of using which material as a reference material, you have to, and you're gonna get same answer on strain. Okay, so it is true at any y, any position, and true at any material location. But depending on the position, after obtaining strain, we gotta go back to the original problem. Once you get the strain distribution, when somebody pointing out stress here, even though the distance from the centroid is the same, stress on brass and stress on steel is different. Stress on steel is twice larger because steel has twice larger elastic modulus than brass. Okay, so please remember this. Okay, so when you consider maximum stress in brass, maximum stress in steel, yeah, you're gonna have different answer, and this is how we approach the composite member bending problem. Okay, so to summarize the procedure, yeah, here we go. Yeah, you have to first convert the problem into equivalent to single material problem. After getting the equivalent to single material problem by tuning the width of the material using one material as a reference, then after solving this problem, you have to obtain the normal strain distribution, which is simple linear distribution from the single material problem. After obtaining the normal strain for each infinitesimal area as a function of y, you can obtain the stress at specific position by multiplying the Young's modulus at the point I. Okay, so this is the procedure for solving a composite problem. Okay, so with that, let me finish the lecture for today here, and I'm gonna see you again in next lecture.